for NB-IOT, with a focus on its architecture, communication, prototype tools, and physical layer design. My name is Jonathan, and my partner is Panaiqi. This presentation is based on our course topic in digital communications. In this talk, I will explain what NB-IOT is, why it is needed, and how it works technically, and what its future development may look like. Here is the outline of my presentation. I will divide the talk into 5 parts as shown. Now let's start with the first part. This part introduces the background of NB-IOT and explains why this technology was developed. NB-IOT stands for Narrowband Internet of Things. It is 3GPP standardized cellular LPWA, low power wide area technology, and it means NB-IOT is designed for devices and need to send only a small amount of data, but need to work for a very long time and over a wide area. According to the PPT, NB-IOT is designed for 4 main goals. So why this is important? Because traditional LTE or even newer wireless systems are often too complex and too expensive for many simple IoT applications. For example, a smart water meter does not need high-speed video transmission. It only needs to send a small amount of data, maybe once every hour or once every day. So conventional LTE and NR are in many cases over-designed for low data rate IoT services. That is why NB-IOT was created. It keeps the important advantage of cellular systems such as license spectrum and operator management, but simplifies the design for low-rate IoT devices. In short, NB-IOT is a technology spectrally designed for simple, low power, low cost, wide area IoT communication. Next, I would move to the socio-economic context. This part is important because communication technology is not only a technical issue, it is also related to cost deployment, industry demand, and social impact. The first reason why NB-IOT is needed is cost. This PPT points out that a low total cost of ownership is critical. This includes 4 kinds of this. This is very important in large-scale IoT deployment. For example, if a city installs hundreds of thousands of smart meters, even a very small increase in the cost of each device can result in a very large total cost. Also, if batteries need frequent replacement, maintenance becomes expensive and inconvenient. Another important advantage is NB-IOT can reuse existing cellular infrastructure. This means operators do not need to build a completely new network from the beginning. This is what we call greenfield deployment, which usually requires much more money, time, and resources. So economically, NB-IOT is attractive because it reduces both initial development cost and long-term maintenance cost. So the second important point is license spectrum. Why is license spectrum important? The PPT gives several reasons below. This is different from some unlicensed spectrum IoT technologies, where interference can be more uncertain, but utilized municipalities and industrial operators, reliability is very important. We use IoT for water battery, storyline monitoring, gas system, or industrial sensing. Unstable communications may cause serious problems. These users usually care about reliability, security, and long-term operations than about very high data rate. Now, let's look at the social impact and risk in the IoT. For the positive impact, the PPT lists several applications areas below. These applications can improve efficiency, reduce waste, labor and smarter city management. For example, in smart agriculture, sensors are monitoring soil and environmental conditions. In environmental sensing, devices can track temperature, humidity, or pollution levels. In public infrastructure monitoring, devices can help detect failures early. However, there are also risks and challenges with emissions. These. This means that although NB-IoT has many benefits, it is not perfect. It is very large number of devices try to access the network at the same time. Signaling congestions may happen. Also, if security is not handled well, connected IoT system may create new vulnerabilities. So when evaluating NB-IoT, we should see the both sides. It brings major social benefits, but its cost introduced technical and operational challenges. Next, I will talk about communications protect tools. This part explains how NB-IoT organizes different functions and in the protect tool step. According to PPT, the NB-IoT protect tools can be divided into user plane and control plane. The user plane mainly includes this. The control plane includes this lower layers aspect, but I also added these two, RC and NOS. Well, we can understand this way. The user plane is mainly responsible for actual data transmission. Control plane is responsible for signaling management and coordination between the device and the network. This separation is common in cellular systems because communication is both data transport and network control. Now let's look more closely at the control plane. The PPT gives three functions. First, NAS or non-access structure is responsible for those questions: authentication, mobility management, session management, interaction with core network. So NAS is more related to connection between the user equipment and the core network. Second, RC or radio resource control is responsible for those steps. Connection establishment, release systems information, wireless resource control. This means RC designed how the wireless connection is set up and management. Below RC and NAS, we still have those four. This lower layer handles the actual transmission over the ear interface. So the control plane is essential because before the device can send useful data, it must first establish, manage, and maintain a valid connection. Now let us look at user plane. The PPT explains the flow of each layer. First, PDCP handles the header compression security. Header compression is useful because the IoT usually sends very small payloads. If headers are too large, the transmission becomes inefficient. Second, RLC handles segmentation, resembling retransmission mode support. So if the data is too large and transmission conditions are not ideal, RLC helps organize and recover the data. Third, map handles scheduling, logical channel multiplexing, RQ, and related control. This means map decides how radio resources are used. Finally, pitch-wise, the physical layer handles modulation, coding, mapping, synchronization, transceiver function. So the user plane is the path used for real data delivery, while each layer contributes a different function to make transmission efficient and reliable.
My name is Pandaichi, and next I will introduce part 4 and part 5. Okay. The part 4 is the technical context and the physical layer of NB-IoT. The part is very important because the physical layer directly determines how NB-IoT achieves deep coverage, low power consumptions, and reliable communication. First key point is that the core design feature of NB-IoT is the 180 kHz carrier frequency. This means NB-IoT uses a very narrow bandwidth compared with ordinary cellular system. The slide also includes an important idea shown in the figure. The sample duration is related to the subcarrier spacing by the formula Tu equals 1 over delta F. So when the subcarrier spacing becomes smaller, the sample duration becomes longer. For example, when the subcarrier spacing is 50 kHz, the sample duration is about 6.57 microseconds, but when the subcarrier spacing between 3.75 kHz, the sample duration becomes about 266.7 microseconds, which is much longer. As the slide points out, the 3.75 kHz model has longer samples and narrow singleton, so it's more capable of sustaining weak signals. Next, we explain the waveform design for the downlink and uplink. According to the table, the downlink uses OFDMA with 15 kHz subcarrier spacing. The design goal is sample scheduling and multiplexing. For the uplink, NB-IoT uses FDMA with 50 kHz or 3.75 kHz spacing. The design goal here is lower PAPR and better power efficiency. PAPR means peak to average power ratio. So the design idea is very clean. On the network side, the system emphasizes scheduling efficiency, and on the terminal side, it emphasizes energy saving and hardware simplicity. Okay, next, let's introduce the physical channel. The first part is synchronization and cell search. Here, the key signals are NPSS and NSS. Their functions are time synchronization, frequency synchronization, and acquisition of the cell ID. The second part is broadcasting and control. The slide shows two important channels, NP-BCH, which carries the basic information of the broadcasting system, NP-DCCH, which carries scheduling and control information. In short, this slide shows the first stage of communication. Find the cell, synchronize with it, read the basic system information, and receive control instruction. Let's continue with the physical channels, now focusing on data transmission and random access. For downlink and uplink, the slides list two important channels, NPDSCH, which carry system information, paging, RAR, and user data, NPUSCH, which carries uplink data and control. They also introduce NPRACH, which is a random access programmable. Its function is very clean. Just means I want to access. After that, the network responds with RAR and the UE process to the normal uplink process. This shows the second stage of communication. After synchronization and control decoding, the system enters data exchange and random access procedure. This gives a full physics layer procedure flow. The process starts from RF and baseband, then goes to signal using NPSS and NSS, then to broadcast on NP-BCH, and then to control on NPD-CCH. This means that terminal first detects the network, synchronize with it, receives the system broadcast, and then decodes cultural information. After that, the flow branches into two directions. One direction is the low-link data path, and the other is the random access and uplink path. It actually shows the complete logic of NB-IOT communication. The first step is synchronize and identify the cell. The second step is receive system and cultural information. The third step is access the network. Fourth is exchange data, and the fifth is enhance reliability. Finally, save energy through sleep-related modes. This is actually how NB-IOT balance coverage, reliability, and battery life. Okay, next we will talk about the core physics algorithm. I will show the meaning of each part in a simple way. It's the first item is the NPSS representative expression. It's a carefully designed synchronization sequence with a basic mathematic structure. The second item is the CNR boost brought by repetition. The slide gives the relation that the effective SNR increase with the repetition number R, and in intervals the gain is approximately 10 log 10 of R. The third item is the effective rate approximation shown in the figure. The physical meaning is the effective data rate decrease when repetition increase, and is also influenced by payload efficiency, changing code, and cultural overload. The fourth item is the random access success probability. The expression on the slides show that the success probability depends on the number of termination and the number of available access opportunity. So this explains four important physics ideas: synchronization, sequence design, and repetition again, and then rate versus reliability, and trade-off, and random access contention. Okay, now I will introduce part 5, which is the future evolution and conclusion. This not only tells us how NB-IOT may go in the future, it also shows the development pace from standardization to mutual physics understanding, and then to integration with satellite and future 6G scenarios. The mention of delay and Doppler is especially meaningful. In satellite based on no terrestrial scenarios, propagation delay is much larger, and the Doppler effects are more obvious than in terrestrial networks, so future NB-IOT system may need stronger synchronization and access designs to maintain performance. According to the table, so we will talk about application strengths and limitation. According to the table, NB-IOT has several important strengths, like very strong coverage, low cost battery power, uplink, and so on. And these strengths make NB-IOT very attractive for practical INT systems that need long battery life and stable network support. At the same time, the slide also lists its limitation, like long effective throughput, high latency, and so on. These limitations are also consistent with the precious technology discussion, like, for example, the low effective throughput is related to the narrow bandwidth and the repetition. So, as the centers at the bottom of the slides, NB-IoT is the best suitor for low-rate, delay-tolerant, long-life IoT application. Finally, let me conclude this presentation. As summaries on this slide from the economic point of view, NB-IoT enables low-cost and long-lifetime IoT deployment. From the protocol point of view, it provides a simplified but complete framework for access and data delivery. For physics aspect, its narrow band design, low PAPR uplink, and repetition mechanism gives it strong coverage and energy efficiency. Therefore, NB-IoT is very suitable for massive delay-tolerant battery-powered wide area IoT, though it has trade-off in throughput and latency. Okay, this is the end of our presentation. Thank you for your listening.